Good afternoon. My name is Bekele. I'm from Imperial College London. I'll be presenting some of my work on modelling the buckling behaviour of mechanical metamaterials, and I'm supervised by Professor Amy Waddy and Dr. Andrew Phillips. So I'll start off by introducing the work, followed by the research aim and some of the work done thus far, and then finish off with some applications and future work that will follow. So what are metamaterials? Mechanical metamaterials, which this research focuses on, are materials that have characteristics based on their microstructural setup, which then affect their macrostructural behavior. These are often dictated by the shape, the geometry, and or the orientation of the repeating structures. So here we've got an example of a hexagonal lattice, which can be used as a structural form which has high strength to weight ratio due to its geometrical configuration, but also due to its porous nature, it's got low density while still maintaining a certain level of structural integrity. There are various types of microstructures. Here we've got examples of two-dimensional ones. So starting from the hexagonal honeycomb structure, the hexachiral, which is a mixture of the hexagon and the chiral geometry, the arrowhead, and some star-shaped ones as well. In this research, we've been mainly focused on the hexagonal type, so that being the conventional hexagon. So as you can see from this figure here, the conventional one has got a positive Poisson's ratio, which means that if you expand it in one direction, you get a contraction in the other direction. Alternatively, we've also got the auxetic honeycomb, which has got a negative Poisson's ratio, and this is purely due to its reentrant corners, which when you're expanding it in one direction, you actually get a global expansion, and if you compress it in one direction, you get a global contraction. So the research aim is to understand the elastic deformation of these types of cellular structures under large deformations, as well as with varying loading and boundary conditions. This will then help us to analyze the load carrying capacity, and the modeling has been done analytically for small scale models and numerically for both small and large scales, and some experimental work will follow as well. And upon having a clear understanding of how these type of cells behave, then we can tailor them for a desired application, such as energy absorption or blast resistance. Initially, we looked at a unit cell, so here is an auxetic hexagon, whereby we loaded it equally at the top two nodes, and another one where we have applied unequal loads at the top two nodes. So the unit cell is set up using members that are pin-connected and rotational springs at the vertices as well, and the bottom two nodes are either pinned or pin and a roller, allowing lateral displacement. And these types of loading and boundary conditions have been chosen in order to replicate a scenario where this unit cell is among a large array of cells. And then the equilibrium parts were then calculated analytically using a total potential energy formulation, which comprises of the strain energy from the rotational springs and the work done by load. And an equivalent model was also set up using a finite element software, and it's generated using beam elements which are pin connected to allow free rotations and rotational springs as well. So model comparison for an equally loaded unit cell shows a near perfect match between the analytical and the numerical work, as you can see from the load versus rotation plot. When the boundary conditions were altered in order to allow greater degrees of freedom, as expected, we saw some bifurcations of the initial path, or the equilibrium path, from the analytical model. Numerically, we tried to replicate this initially by adding some geometrical imperfections to the system. But as you can see, there are some discrepancies between the analytical and the FE model. And this was due to the fact that the FE was based on beam elements which had a given large stiffness, whereas the analytic one assumed rigid elements with infinite stiffness and no strain. So seeing these types of differences even at a unit scale level was quite important, and especially when we're trying to upscale to larger lattices to see what sorts of differences we'll get. So moving on from there, we've been looking at sandwich panels. As you may know, sandwich panels are composed of two stiff face plates and a lightweight core structure. The flexible core often allows greater shear capacity and can also have added functionalities such as insulation. Here there are examples of two types of cores. The first one is a foam core, and the second one is a periodic hexagonal lattice form. We're more looking into the second type of core structures. although what we are proposing are three-dimensional cores that can move independently, as opposed to a two-dimensional lattice that you see here that's been extruded in the third direction. And in terms of the features, I just wanted to highlight, often with sandwich struts, the failures are seen as a disadvantage, but by using these types of microstructures in the core, we're trying to use the failures as to our advantage, basically. So there's already an extensive amount of research done on buckling of sandwich struts. Here is work done by one of my supervisors, Aimer, on the interruptive buckling of sandwich struts under axial compression. There's a picture there, as you can see. This is the load versus end shortening plot. Initially, you see a linear relationship between the load and displacement, and this is representing the pure compression case of the strut until a point C, which is the critical bifurcation point, corresponding to the critical load. Above this point, you start getting global effects, so an Euler-type bending of the sandwich strut. Subsequently, you reach a point S, which is the secondary bifurcation point, and beyond this point, you start seeing localized effects on the bottom faceplates, such as the wrinkling that you see there. And by changing the different parameters, such as the length or the depth of the panel, you can alter the load capacity as well as the onset of global and local modes. So the question here is, can we trigger the different buckling modes through changes to the core microstructure? So either having uniform cores or hybrid cores, which are a mixture of the different geometries that I stated earlier. We've been looking at 5 different models. So the first one is the conventional honeycomb lattice, the auxetic honeycomb with the reentrant corners, the conventional honeycomb with 4 vertical auxetic inclusions centered with the conventional, the auxetic equivalent, so with the 4 vertical inclusions centered with the auxetic, and lastly, the suitably named CIA, which is the conventional with intermittent auxetic inclusions hidden around the top and bottom faceplates. So first we've got a comparison of the purely auxetic panel with the one with the conventional inclusions. Here are some animations of the deformation. So the top one is the auxetic panel, and the bottom one is the one with the inclusions. The section forces are given here, and the dark blue shows compression, the red shows tension, and the neutral regions are given by a light green. As you can see, the purely auxetic one behaves more commonly with global effects seen at the top faceplates initially, followed by some localization. And you could see some lock-up effects in the central midspan section at bottom faceplates, which inhibits the panel from displacing much further. Whereas with the one with the inclusions, the transition between the global and local effects are much more smoother. And you can see that there's an increased end shortening, which allows it to displace further, and it's got a more of a ductile-like behavior. Next, we've got a comparison of the conventional, so the purely conventional one, and the one with the auxetic inclusions at the bottom. So again, you can see the inner structure for the conventional one is mainly in compression, the top face is under tension, and you see some wrinkling occurring at the bottom faceplate as well. Whereas the localized effects in the one with the inclusions are much more pronounced, and so the amplitudes of the wavelengths are much greater. But what is quite significant here is the reduction in the load carrying capacity just by having these inclusions. However, you do get a much greater area under the graph by having these inclusions, so an increased energy absorption capability by having these. In both cases, I just want to reiterate, I say ductile-like behavior because we're more looking into the mechanical behavior and not material defects. Next, we have the conventional, as you've seen already, and one with the intermittent inclusions. What's interesting here is the potential for reducing the dropping capacity that we saw earlier just by having the inclusions in this manner. But we do see some snapback instability, which we need to investigate further. But what we thought was quite interesting is when reducing the panel length. So here's the top one with the purely conventional panel, and this is the one with the intermittent inclusions. So often when you reduce the panel length, you alter the load capacity as well as the plateau region between the critical and the secondary bifurcation, whereby if you carry on decreasing the length of the panel, you get to a region where the global and local effects occur simultaneously, which is sort of seen in the top panel case. In the bottom panel, you could actually see the plateau region has extended quite substantially, and this is because we're seeing some local effects at the top face and the bottom through the snaking behavior that you saw, and this led to local effects occurring at the top and the bottom face, and therefore much more end shortening and greater energy absorption capability. Then we further reduced the length of the panel. And actually you could see that there is a slight increase in the load carrying capacity just by within the one with the intermittent inclusions, as opposed to a drop that you see with the, with the case of the purely conventional panel. So in terms of applications, the obvious one to choose is blast resistance. There's already a group in Melbourne looking at auxetic panels for blast applications, but what we aim to do further is to be able to tune the buckling behavior through having inclusions or hybrid cellular structures, and therefore be able to redirect the energy that is from impact towards the outer regions, for instance. Another field would be the biomedical field. So this is work done by a group at TU Delft, whereby they're looking at layering the auxetic and the conventional lattice one on top of another for a hip prosthetics to deal with a septic loosening issue that you often get with prosthetics after a certain period of time. Again, we could look at utilizing the crumpling behavior that I showed just recently for, say, knee prosthetics, whereby if the patient is to fall or land in a certain way, then the energy is absorbed and so the force is not transferred to the adjoining bone structures. So in terms of future work, we're looking into expanding to 3D lattices. We've already started looking at different orientations for the intersections, and upon having a 3D model, then we could 3D print and do some experimental tests to validate the numerical work. So just to conclude, we've been investigating the mechanical behavior of lattice microstructures to tune the buckling behavior. We've been mainly looking at the elastic properties, but we'll also be looking into material buckling properties. In terms of the geometry, we're looking at mainly the auxetic and the conventional hexagons. And the modeling has been done numerically using a finite element method, analytically through total potential energy formulation, and some experimental tests will follow as well. And in terms of application, we'll mainly be looking into blast resistance and biomedical uses as well. Thank you.